Hi everyone, welcome back to Calculating Building Peak Loads in Trane Trace. Again, this is Neil Bulger, and we are going to look at reading the results and making sense of the outputs. There are lots of outputs to look at, so we're going to start with the most high-level reports that come out of Trace, and then go further as we start to look at some other ones. So, with that, let's go back to our model. I stopped us right last time in the right after calculating results. Almost clicked on view. So actually, let's go back. So if we had not run results before, we could resimulate. And if we already have run the results, we can come in here and just hit check the ones we want to look at and hit view results. So this little window is all the different reports that can come out of Trace. These reports can come out as PDFs, Excel files, multiple versions of Excel files actually, so some are more useful than others in being able to make sense of how to import them into Excel or not. So we're going to start with the system checksums and the room checksums. Overall, the design reports tab has a lot of high-level reports for you to be able to quickly look at the model. The detailed reports go into individual components. The building envelope loads at a certain time, the internal loads at a certain time. And we'll look at these a little later. For now, let's spend most of our time looking at these. Yeah, so we will continue to come back to this level. So I checked those two. I'm just going to hit preview action. I'm not going to hit print. I haven't decided I actually want to save these. So it's going to load them up. At the top you see two tabs. System checksum is here. I only have one system, so there is no list. There's a group tree here, you can see. If I expand the group tree, if I had more than one system, there would be multiple ones in there. The room checksum looks exactly the same once it gets loaded here. Starts with the first room on our tree, and you can see there's a blue arrow to go to the next room. On the next room, I could leave the little tree open. We could see our three rooms. So these reports between the room and the system look exactly the same. I'm going to start over here on the system side of things, and then we're going to go back to the rooms. So what are we looking at? There's a lot of information. So the system checksum is really meant to be a one-page report, very technical information that can be used and reviewed and do a lot of different things for a design project and a reviewer. So we're going to start off, so there's a lot of different reports. There's this breakdown report of the cooling coil peak, cooling space peak, and the heating coil peak. Each one of those is a different time of the year when the building was under a certain peak condition, and it's shown here, the different breakdowns of the components. We're going to dive into this. At the top right, the temperature box talks about what the temperatures were when the model ran, what it supplied air at, what it returned air at, and any other critical temperatures. Air flows. This is the box that will show you how much airflow is coming through the main fan, how much is contribution of the ventilation system. There are a lot of other things like secondary fan, diffuser, minimum, I don't know, a lot of these auxiliary. A special point to note about all the inputs on this whole report, this is a default report from Trace. And if an input is not necessarily valid for our system, for example, we have passive chill beams. If we didn't have a return air plenum, it doesn't mean that Trace isn't going to report a value. So it will still report a value as if we did have a return air plenum, because this report is sort of fixed. This is how it's set up, and it's always set up this way. So know that, because sometimes you'll see numbers in here and say, wait a second, we don't have underfloor supply heating package something something. It's like, no, you don't. It's at 0. But that word is always going to be on this report, because that is how the report comes out of the machine. Moving on, engineering checks. These are very useful metrics that you will become more familiar with as you do more peak load calculations. And they are helpful in the sense of being able to quickly look at them and go, nope, this model doesn't make any sense, I better go fix it. everything from CFM a square foot to the square foot per ton to the BTUs per hour per square foot. And the number of people. Number of people is key. There's some other ones as well, the area, the heating coil selection. Oh yeah, these coil ones. So again, we're going to go into this report. These coil selections are really not that important. These coil selections are essentially trace plane engineer. They are trying to pick what they think the right size of a coil would be. I would really recommend sizing your own coils and working with a representative to do that, and really not relying on this peak load. So with that, let's dive into the interesting stuff. So let's start with the cooling space peak. So this is the peak inside a room or inside the entire building when the internal loads are hitting their highest amount. At the top, this is occurring on the 9th month at the 15th hour, and the coincident dry bulb at that hour was 83 degrees. We can see the breakdown of the envelope loads in BTUs, and then we can see the breakdown of the internal loads. You'll notice down here that there is no infiltration at this hour or ventilation. And actually, we're using these passive chill beams. I think we'll rerun it with VAV. But the space peak is really just when are the internal gains and the envelope gains the highest. And if we were to look at a picture of what this really looks like, what does this entail? If we were to draw our little box, and here in our little box we have represented all the different heat loads we might see in our building. We have people inside, we have equipment that's giving off heat, we might have lights that are on giving off heat, we have conduction and convection through the envelope if it's hot outside and hot air is trying to conduct its heat through our rated R value roof and wall. That will contribute to the load. We have our direct solar gains, both hitting the surface and warming the surface of the roof or the walls, and then also transferring all the way through our fenestrations and onto the floor. And then we have our fresh air. And so when we talk about space peaks, we're really talking about the peaks that are occurring inside the space attributed to the envelope and the internal loads and often the infiltration. And if we were to draw a little box around this, I've shown here this little dashed red box. And so this is really important because it really is a hard concept to grasp, and it took me months to multiple tries of, I think I understand space peak. So the space peak is used to determine how much heat is built up in this space and how am I going to get that heat out of this space. So it's really a question. The reason we look at these numbers is to size the quantity of air, or if we had a radiant system, the flow of water, if we knew what water temperature was coming in and out, and how big those manifolds or those ductways need to be. So I've kind of captured the diffuser in this cartoon diagram, because in this cartoon we would really want to know how much CFM do we have to push out that diffuser if the CFM coming out is at 55 degrees, I'm making assumptions, and I want to keep the space at a 75 degree temperature. So we would be able to say, okay, I know I'm going to supply 55, I know I'm always going to remove 75, so I know the change in temperature will be 20 degrees, and I also now know the load because I can add up all these things. I can add up the people, the lights, the equipment, the conduction, and the sun, and now I can just figure out a volume of air and therefore the size of that diffuser. And so that's really what the space peak has to do. It's completely agnostic of the ventilation air. The ventilation air doesn't change the size of that diffuser. It could if the load was very low. Maybe the diffuser has to become bigger if the ventilation air was higher. Yet the amount of energy needed to cool down fresh air is not relevant at this point. It's the amount of energy required to cool down fresh air doesn't change the size of your VAV box. and I'll explain why. So now if we look at the coil peak, so this is the envelope, this is all the loads in the space. And now if you've noticed here, I've sort of included ventilation. And the coil peak is the peak that we would want to know when we start to size the central cooling coil or the whole system cooling tonnage, whole system size tons. I would say, let's say AHU central coil. We would actually still use the space peak would be for the AHU fan size. But the coil peak would need to include the fresh air. And so if we redraw our little boundary, let me bring my text with us that I just changed. So what's going on here? So we redraw our boundary. So now our boundary includes the fresh air contribution. So now if it's 80 degrees outside and we need to balance our room at 75 degrees, we need that cooling coil to have enough capacity to be able to condition the volume of fresh air from its critical temperature to the space thermostat's temperature. So that would be 75 in this hypothetical scenario. And so you can almost imagine the coil peak as all the other ones plus the space plus ventilation. These coil peak and the space peak may not occur at the same time. And that really has to do with the shading of a building most often. You may get a space peak that is coming in the winter when the sun is lower in the sky. Oh, not going to work. And is not able, and is sort of like missing the shades. If the sun was very low in the sky, and maybe let's say we had a really insulative envelope, the roof was R60 and the wall was R40, and there was no conduction or convection coming through here at all. We're just sort of dealing with the internal loads and then the direct sun. We may see a space peak that occurs in the winter because the sun's low, like I said, it misses the shade. And even though it's 60, 70 degrees outside, that's not really what we're concerned with, because let's say it was 60 degrees outside. Well, the VAV box could still use that 60 degree air, and we wouldn't necessarily have to pay for the tons of cooling to go from a higher temperature down to our supply temperature. Yet the size of box, the size of airflow coming out of that box still needs to be determined, and that is determined based on the thermostat we want to keep and the internal loads. The coil peak, again, is one where now we're counting the fresh air contribution, and now if, let's say, it gets up to 90 degrees in the summer, even though the sun is higher in the sky, because we now need to bring outside air from a hot temperature down to our thermostat, the combined amount of cooling for fresh air and for managing the sun and all the internal loads could result in a larger tonnage than the winter time. Because in the winter the air was cold, but the sun still came through. So the space peak could size the VAV boxes to manage their individual flows. The coil peak will size our coil itself and the tonnage of a building or a chiller or the whole apparatus. And so if you look at these two, let's actually rerun trace, because I think I changed the system to chill beams and it's doing some funny things. So let's go back. We're going to pick VAV with reheats. We're going to apply that and we're going to calculate real quick. There it goes, all the iterations. All right, now we're back in business. System checksum, room checksum. All right, so here we go. So our space peak. Now our space peak is showing we have internal loads, we have envelope loads. We can see the direct sun contribution is this. And this is occurring later in the year. The sun is higher in the sky. It's 3 o'clock when this occurs. Our outside air temperature is 83, so It's good to know. And if we start to look at the coil peak, we can actually see this occurs earlier in the year, occurs in the 8th month, and it occurs later in the day, occurs at 5 o'clock. And actually what's happening is our glass solar is higher here than it is here. So I think the sun must be coming around the corner and more of it is going into the room. And even though the coil peak has 80-degree outside air compared to our space peak at 83, because the direct sun comes in, this ends up being the highest load. Here, the coil peak, we can see we have ventilation. So if we were to take on the right the nominal ventilation, 1,110 CFM, and we were to times that by the change in temperature between 80 and 75 times 1.08, we would see a BTU value around this. Trace might use 1.1. This is yeah. This also says net total. Could be that this is also an enthalpy. So, but it should be that you should be able to hand calculate this exact value based on those temperatures and that airflow rate. And if you're not within, a few percentage points, then redo your math and figure out what's going on. Let's see. Reading these reports too, you can start to see percent of total. So here we can see the direct sun, 31% of this building. Infiltration, 21%, quite high. Our internal loads total, 31% of the coil peak and 40% of the internal loads. That's pretty high. Sometimes it's also good to do some density checks where we take the total BTUs of people, for example. You can even take, here's just the sensible, so if we take 22250 and we divide by the number of people, 90, we can check, that comes out to be 247 BTUs a person. Likely this 90 person is rounded, it's maybe a smaller number slightly. But that's about what we would expect, 250 BTUs each. Probably different, I think, I don't know why, but different spaces had slightly different inputs. Let's see, the square foot per ton, so we're at 500 square foot per ton, pretty average. I would say most generic buildings that have poor envelopes can be close to 300 square foot per ton. We really want to aim for 1,000 square foot per ton as our design goal for all our buildings. And it is climate dependent, so that may not be possible in the middle of India, but you never know. So those are the kind of things I'm looking at when I look at a trace report. I'm looking at the supplier temperature, I'm looking at the heating air temperature, does that make sense? Because down here, the 90 will dictate the quantity of air needed in order to maintain the building. Other things to look at, we can also start looking at the room check sums. So in this one, they look exactly the same, but now what we're looking at is when each individual room found its peak. We only actually have 2 rooms with walls, and then we have 2 rooms without walls. I set up infiltration to be in all spaces as a simple air change rate, which sometimes is a bad way to do it. And here we can see we have infiltration in what is supposed to be interior spaces. So not something we might want to change. Here is our IG office area. Oh, that's right. I only have 1 space actually with exterior walls. So it's actually at the exact same time the whole system is peaking. If we had a direct east room and west room, we would be able to see those. But yeah, that's kind of what to look for. The other thing to look at is the percent of outside air and the total airflow density. Again, the amount of airflow density is the same sort of magnitude as like the square foot per ton value. So traditionally, we'll see air-based systems be 1 to 1.5 CFM a square foot. Fresh air might be less, around 0.15 to 0.3 CFM a square foot, depending on how much fresh air you're bringing in. Those are some just good things to check overall. But generally, I would say the cooling loads here look really spot on for a typical office in our Alameda climate environment. The heating loads, we can start to look at these and see the space heating capacities and then the ventilation included heating amounts. Heating just occurs when there is no outside direct radiation and it's at the design condition. So there's no date associated with the peak heating value. It just is always 40 degrees. It also assumes that it's the worst scenario. So there's no internal loads and all our fresh air is coming in. Some other things to think about. We haven't taken diversities, and if we did take diversities of people, meaning we took a diversity saying at the system peak, not everyone is going to be in the building, and we want to account for that, we would actually, the number of people here would not change. This report always has the maximum number of people, even if we took a diversity. The way you would check is I would recommend looking at the BTUs of people and dividing by a certain known BTUs per person that you designed for. And that will tell you what actually is being used when this coil peaked or this space peaked. So if we took 50% diversity, we would see these BTUs reduce, and I would then check and say, well, over here the engineering checks say 90, but I know that each person is only 250, and if now there's only 11,000 BTUs, how many people are really in my building? That's how you can check this report. This report could still be useful. There's other reports where you could actually see the number of people change in the detailed section under internal loads. But generally, that's the one I would look at. So those are the two main reports. If we had thermal zones, they would look exactly the same as those other reports, but for now, we don't. You could also look at design air flow rates if you're doing ventilation in here. If you want to see a standard 62.1, if we had done ventilation that way, this report would show those things. There are a lot of other reports. You can also see just the building envelope loads. Let's see, some of the useful ones can be the design cooling loads, design cooling capacity system. I don't remember. Let's look at a bunch. We're only going to poke around these shortly. Design cooling loads. Same information we looked at, just kind of spelled out a little more. System component selection. Loading. Yeah, maybe not. That's not too useful. That's trying again to play engineer. This one. It's just going to tell you the one tonnage that Trace assumed and sized with. Here, this is actually a really useful report. Peak cooling loads, main system. Here it will list out all the different rooms, the floor area of that room, when each one of those rooms peaked, and their loads. And you can also see the peak time. It changes for these different coils. It will then show the peak, and this number, this 88 or 227, this is actually the sum of the peaks, which is a terrible number in the sense of if you were to add up all the rooms when they were in their worst situations, what would that number be? And then you can actually see if you were to find when the whole building peaked together, what is that number? So that number is often less. Here they're very close because we don't have that many rooms. But the sum of peaks is not always a useful number to look at. I'm struggling to think of a system of why you would want to see the sum of peaks. But this is where you can see the block peak. So the block peak is sort of the diversified peak, or the diversified number that occurs when the sun is in the worst position for the whole building, not just for one room. Sometimes you'll room, yeah. So building area. There are a lot of reports, and we've actually made a very large spreadsheet that can take a lot of these outputs and dump them into Excel. There's a spreadsheet we made where we output all these as certain Excel file types, import them into Excel, and are then able to build on that. And it's really useful for large jobs. If you're working on a job, say 8 buildings and 1 million square feet, I might recommend considering something like that. But if you're not, then keep it in Trace. That's all for reports for now, and we will go on to talk about archiving and